I'm Dr. Pete Seal, professor in journalism here at CSU. This is my sixth FutureVisions. We started back in 2005. Just a really quick story. Back in 2005 at the first FutureVisions, we had a speaker from HP named Bob Gann. And Bob Gann gave a talk on the future of visualization. And in 2005, Bob Gann predicted that in the future we would have one camera that would do it all. One camera that would take stills, one camera that would do video with equal quality. And he said there is no way one camera could ever do that. One camera to do it all. In 2007, the iPhone came out, end of debate. So things people have been talking about since FutureVision started have now come to pass. So things you're hearing today, you'll probably be seeing evolve over the next 5 years. And that's what we asked our speakers to do, look ahead 5 years, 2018 to 2023, and predict their vision of the future. So I'm pleased to introduce our next speaker. She's Beth Plale. She's a PhD. She's a professor of informatics and computing at Indiana University, which is my alma mater for my PhD. She lives in Bloomington, Indiana. She's on loan right now for 3 years to the National Science Foundation. So she's living in Washington, and she's a science advisor for public access for the National Science Foundation. So she's been conducting interviews with other folks here while she's here, and we're very pleased to have her here as our next speaker. Her topic is big data. And big data, you'll know it because it's called the U.S. Census, coming out soon, big data. Also, CSU is known for hurricane predictions. We've been doing that since Bill Gray was doing it 15 years ago. And that's definitely big data. And they're predicting 14 hurricanes this year, an active hurricane year. 7 of them will hit the United States. So this is big data as it influences people's lives. So I'm pleased to introduce Beth talking about big data. Welcome.
Great. Hello, everyone. It's great to be here. I really appreciate the invite. Where am I pointing? Just okay. This is a talk on big data and open science. I am, as Pete mentioned, the science advisor for public access at the National Science Foundation. The thoughts and opinions I'm expressing here are my own thoughts and opinions. So open science is a term that's been used internationally. It's been endorsed by governments to describe economic and societal benefit that comes from just a continued stream of scientific discovery that has basically been delivered since, mostly post-World War II. A new piece of that is the data piece, and this captures open science, today's data, tomorrow's discovery, and there's actually a document at the National Science Foundation that's labeled just this. It's this public access plan, and it implies that data that are produced today are the basis of discoveries tomorrow, and that underpins much of my belief. So open science motivates everyone that's carrying out research to be more attentive to the public availability of or openness of the products of their research. And that's publications, which we have a long history with publications, and we get our access primarily through library subscriptions in the university setting, but also the primary data, the physical samples, software, and other supporting materials. All of this falls under the open science umbrella. The trajectory of research, as many of us know, is international, and it's highly collaborative and interdisciplinary. And what does that do for the individual who is carrying out their research, perhaps through their own funding in this larger context? And how are they a good open science citizen in this larger context? So looking at this from the perspective of NSF as a funder, so the National Science Foundation encourages open science, and it does so with policy language like this. Investigators are expected to share with other researchers at no more than incremental cost within reasonable time the primary data, samples, physical collections, and other supporting materials created or gathered in the course of work under NSF grants. So a person who is funded by an agency like the National Science Foundation, NIH is not much different, NOAA, NASA, DOE, these other funding agencies, that this is the open science obligation. And then there's an expectation. And the way in which that's brought about is through the data management plan. So a researcher, when they write their proposal, their 15-page proposal description, they include a data management plan. And here they identify the products of their research, the non-publication products of the research, and how they expect those to be made openly available. And these are the products that they create during the course of their research. This then, and that becomes a document in their grant proposal. And then while that grant proposal is going through merit review, the data management plan is examined. So this is an opportunity for the community of your peers to give input to whether or not how you say you're going to take care of your data is viable from the community's norms. So this is the context in which an individual researcher works. So let's look at this in the context of big data, and there's a point I want to make here. So we're going to look at this from the context of a single organization, and then what I call this mid-scale infrastructure. So we've got, let me see if I can get a pointer here. Okay, so we've got a typical abstract computer science abstraction here. It's actually coming out of MapR, so the diagram that I found. Okay, so there's a data lake. It's a concept of data flows into this lake. You could call it a warehouse. Data lake is the new term for it. And in that data lake, it undergoes life cycle management. There's transformations that take place. The lineage of that data is important to capture. Where did it come from? What kind of data is it? The data sources are multiple. Again, this is in the context of a single organization. This could be, a single large project at a university. It could be, a company. This diagram happens to capture the company setting better. The data are coming from, relational databases, documents, emails, social media, blogs, tweets, link data, clickstream, sensor data. And the notion of the data lake is that all that is flowing into this data lake, and then analysis that takes place, which is shown on the right-hand side, is taking place over all of this heterogeneous data that's in the context of this data lake. And then there's actions like auditing that take place. So this is a very viable big data architecture and set of sources and actions in the context of a single organization. And when you're doing that, we look at the inputs and the outputs, because let's focus on the inputs and the outputs. Those inputs, those data sources, could be open source. Some of them may be open source, or they're controlled by agreements. And then on the output side, depending on the organization, those products, if it's in the setting of a company, those products are probably proprietary because they're being used for making strategic decisions, or they're subject to the guidance of a funder. So this setting is a well understood setting for activity to take place because the terms for the inputs and the terms for the outputs are well understood. So the first main point I want to make on the talk is this second case, and this is the emerging case that I'm calling the mid-scale infrastructure. And let's look at, we're just taking that same architecture diagram so that it's a familiar one to you. It's still this Hadoop data lake, only now it's taking in fMRI data. And it's doing so from multiple researchers. So we've got researcher Alice, researcher Bob, researcher Carlos, researcher Eve. For those of you who come from the security background, these are well-known characters. And they're each contributing fMRI data to this Hadoop data lake. And they're doing it so that they can carry out analytics that's done over a larger collection than if they were to be able to utilize only their contributions. And this is some imaginary, federally funded project. And they may be using this in a classroom setting. It's now extremely valuable when you can get researchers from multiple sources contributing data into a single collection. So these researchers contribute their data to this fMRI data lake, we'll call it, and then in return they're given use of the entire collection of the fMRI data. Now, this is a win, this is a huge win. But let's go back to that obligation this jumps a little bit, sorry about that. But let's go back to that obligation that that individual researcher made when they got funding from their federal agency. So Bob had written into his data management plan that he would make available, more broadly, open science, the data that his project creates. Okay, and this is the key. He thinks, or he should think, that contributing his data to the data lake should satisfy his DMP. You know, I'm sharing my data, I'm sharing it with the data lake, it's going to therefore be open science, it's therefore going to be open and comply to my data management plan. So he gets to use the larger collection, and he gets to dispense with the obligation under his data management plan. It's perfect. However, the data lake owners are saying, and this is the state of research today, the data lake owners are saying, wait a minute, we do analysis, we don't do open science. And then this is the state, again, the state that we're at right now. We're not an archive, you know, we're not a repository. This is the state of things today. And we see this in academic settings where, you know, we've got our library, and our library is doing their darndest to take data sets and make them available over the long term. And then we've got these active research projects. Those need to come together better than they come together today. So in the case where we've got this mid-scale infrastructure with numerous research contributors and that are guided by separately funded projects and they're contributing, there's mismatched expectations, and that, in my mind, is a big open question today. Okay, point number 2. We talked about data. By 2020, the volume of digital data is going to reach 40 zettabytes. Big number. If you break it down into 1 gigabyte files, which are big files, that is 1 trillion files. And let's call each one of those a data object. So I'm going to convert to the term data object. So we've got 1 trillion data objects. Okay, let's add 1.5 billion projected Internet of Things devices. Those are the ones with cellular service, which are projected by 2020. That gives us 150 billion more data objects. You know, this assumes you're chunking, you know, each device by monthly chunks and you know, so on. There's a chunking there's a chunking behind that. So we had 150 billion more data objects. Okay. We've got 1.5 trillion data objects out there, and let's just suppose science is 1% of that. The research data is 1% of that. How is a researcher who's tasked with something like global diversity supposed to find, say, they're tasked with finding 1,000 data objects from these 11 billion data objects that are conservatively the science data? How are they going to find the science data? How are they going to find the small portion of biodiversity data within that? You know, we can sit back and we can say, well, Google is going to solve all of our problems. Google has their own problems. Okay, so envision something like a data object layer where you've got some network of independent, globally unique, persistent data objects that have relationships between them. So we've got, you know, object A, which is metadata. Object A is metadata for object B, and object B is a revision of object C. Object F is derived from object E, and object G is a part of object F, and D is just sitting out there by itself. So we've got each of these data objects that I pointed out, the 11 billion, we've got these data objects, and they have relationships between them. And, you know, if you recognize this, our computers are linked in this way. You know, they don't have these kind of semantically rich relationships between them, but they're linked like this. Can we envision a similar network of data objects? Some of those are going to be in repositories, so the repositories are entities in this networked object world itself. But the objects themselves should be able to reside independent or have identity independent of the repositories in which they exist. So we have this lightweight data object overlay, which The basis of it is persistent identifiers for data that can, I'll come back to that. And this is a segue to these FAIR principles, which some of you may be familiar with. But going back to that 11 billion object problem, by us as a community advocating for the unique identification of the data objects that we produce, and this is like a DOI for papers, we do a similar thing for the data objects, and we all do it in one or two or maybe three different ways. That's a key step to getting the kind of discoverability that we need over our scientific data. So it's one of the major barriers to our sharing is, we think that an ID that we assign based on whatever we come up with is going to hold globally. It will not. So we need to move as a in the open science community, and researchers and funders and whatnot need to move toward the global adoption of these persistent IDs. And what takes us there are these FAIR principles. Is anybody familiar? People heard of the FAIR principles at all? You got a tiny bit of recognition on. And this came out in 2015 under the umbrella of Force 11 organization. It's caught on simply because it's intuitive. Data objects are findable, accessible, interoperable, and reusable, and that's where the FAIR comes from. And it is a concise and measurable set of principles for scientific data management, so it allows metrics to be defined against which one can measure whether or not a repository or a solution is fair. People often draw a line between the F and the A and the I and the R, and they say those top two are easier than the bottom two to bring about, and that's true. So just going over them very, very briefly, to be findable, number one, the metadata and data are assigned to globally unique and eternally. Eternally, good, okay. I like that. It'll long be beyond my time, but eternal is fine with me. Persistent identifier and data are described with rich metadata, so the accessibility goes a step deeper. Retrievable by their identifier using some standard communication protocol. Metadata are accessible even if the data are no longer available. And the FAIR principles have a very strong machine actionability orientation. In other words, it's not going to be humans with browsers trying to find their data. It's going to be machines working on their behalf to find data for them, machine services. And the metadata formats utilize shared vocabularies, and the metadata and the data are sufficiently well described so that reuse is possible. You got to be able to trust the data. You got to be able to assess its fitness for use. You have to be able to use it. That's probably our biggest challenge right now. So the FAIR principles are a concise and measurable set of principles for scientific data management, as I've said. And while these principles make intuitive sense and there's considerable talk internationally about what they mean, what the FAIR principles mean, there's still, what they mean from a policy perspective is still is an ongoing conversation. So I made three major points. Open science embodied in our research practices not only are, okay, I'm done with it, I'm ready to hand it off point of our research, but embodied in our everyday research that assumes that those objects are part of ongoing research, that open science can be embedded at that point, and that was the mid-scale infrastructure that I pointed out. This exponential growth that we're going to see in persistent IDs. Handles is one persistent ID. It's used to identify baby food containers. It's used to identify movie clips. How are we going to find the research data? So we need this notion of persistent IDs as the first step, and then some type of overlay network which helps us to link things together. And then the wide adoption of these FAIR-like principles are a very pragmatic way to make all science open science. So thank you.